Hello, am I audible? So I think we should start today's. Hello, am I audible? Just you can
Yes,
write.
sir.
Okay, thank you. So let's start today's discussion session. So I think the assignments are released, so we would be discussing those assignments towards the end of this weekly discussion session. So uh, for the first, so let's start with the weekly overview of what. Yes. So mainly this week, the storage devices, the battery energy storage devices, were being mainly focused. So how and when and what kind of need for the storage devices. So the need for the storage devices, and further on there will be classification of the storage devices, and from the smart grid perspective, what kind of other than the battery energy storage devices, what other mechanical storage devices can be utilized to a proper extent so as to maintain the grid operation smooth and all these things. So let's start the today's proceedings. So first of all, what's the need of these storage devices? So first of all, the storage devices allows us to Suppose for the smart grid architecture level, so smart grid monitoring level or smart grid. Yes. So suppose from the smart grid point of view, the location flexibility is a must. So from the location flexibility point of view, if we go into deep, that the battery energy storage devices has this kind of flexibility of being relocated to some places or being established in such a position, and some moving energy means the storage devices can be of moving types and all these things. So in this scenario and other things, like the location should be a proper and justified point of view from the point of need for the storage devices, as location, we based on the various locations or the distinguished features, these energy devices can be placed so as to maintain the perfect energy balance of the smart grid architecture, of the smart grid system. And another point of view is that the variable renewable generation sources. So what we can see is that with the day by day, the variable renewable energy is getting, means the more and more renewable energy is being fed, is being generated, renewable energy generation is getting increased day by day, and it is quite variable in nature, and hence this variable nature of the renewable energy devices, they give the chance and opportunity for the researchers and all these industry experts to use these storage devices, because the the uncertain behavior of these variable renewable, okay, let me see. So from the variable energy point of view, if the renewable energies to store this amount of, because the renewable energy, the uncertain behavior of the renewable energy, they would be feeding the system or as per the weather or the or weather scenarios are concerned, because for the wind or the solar, the cloud covers and all these things, or the wind speed and all these things would be very much effective for the generation perspective. So hence, when we have higher generation and the demand of the grid is being maintained or being fed by the other or the other generation devices, so in those cases, the variable renewable energy generation takes due to variable renewable energy generation, need for storage devices are also must. So also decarbonization is another part, and power reinjection. Suppose we need whether we can reinject the power to the grid as per the demand, as per the necessity, when the renewable or whether when the conventional power generating units are not capable enough to meet the demand requirements. So in those cases, these kind of flexibilities are being there. So the power flexibility, power feeding flexibility, as well as storing flexibility, all these things, and controllability. It gives a higher amount or gives a scope to control these renewable energy or the battery management storage devices. These are controllable in nature. So this history has been taken from where we can observe the fuel cell, lead acid battery, the evolution of the battery energy storage systems one by one. So these are some of this. This is being from the lecture itself. So now coming to the energy storage system. So the energy storage system can be classified into these four categories: the thermal energy storage system, mechanical energy, chemical energy, and the electrochemical energy. So whenever we are keeping the fact of thermal energy storage system, so in those cases, thermochemical energy storage is a part of the thermal energy storage system. Suppose in mechanical energy storage system, we have the pumped hydro flywheel. So pumped hydro architecture, it is a kind of upper dam and there is a lower dam. So from the upper dam, if we if in during the of in the during the peak hours, means the when the load is to be met and the frequency has to be maintained constant. So during those times the upper dam uh, releases the water and it gets stored in the lower dam, and in this process the amount of generation that is being fed to the grid to maintain the frequency of the grid to be constant. And for these all these things, the and during the off-peak hours, means whenever the generation is more and the thermal units can meet the demand and they are being properly, they have to be, means they have their ramp rate limitations. So we can't just generate or means shut down. We can't just switch on or switch off these generating units. So in those cases, these pumped hydro storage systems are quite essential to maintain the frequency of the grid constant, and all these things. For these all these pumped hydro systems, they also get the availability based tariff, means they have to maintain the means, each and every power generating unit gets these kind of facilities. So your main operating principle is to maintain the grid frequency constant. So this is a kind of mechanical energy storage system. And the flywheel energy, flywheel, they can store this kind of inertia of the energy of the grid. They have to maintain presently due to the renewable penetration. So the grid side inertia is being lessened. So due to this lesser amount of inertia, sometimes the due to sudden fall or abrupt fall in the load. So during those times, these flywheels try to maintain the inertia of the system to be a constant, because they have to absorb that, they can absorb that they have the of the excess amount of power from the grid. So and the synchronous generators do have the feature of the inertia of the, means do have the feature of this inertia, because during the higher loading conditions or lower loading conditions, suddenly if the load falls or load rises, the the synchronous generator do have the rotating mass which can absorb the sudden variations, sudden fluctuations of the system, and try to deliver or exert the energy stored in the rotating mass to the system during the off peak, during the sudden during the requirements if demand is high. So these kind of facilities are to maintain the inertia of the system, or to this kind of energy. This is a kind of energy storage system itself, flywheel energy. So now coming to the chemical energy. So we have the hydrogen energy storage, the synthetic natural gas storage, and all these things. The This is the hydrogen, and lastly the electrochemical, where we have the battery and the flexible battery storage system. So mainly our discussion would be focused on the battery itself as the this battery energy storage system. So this is the classification of the energy storage system. So where we can see that the mechanical and the electromechanical, this mechanical part, we have the pumped hydro storage, compressed air energy storage, flywheel storage. Now the this is from this reference, as you can see. The electromechanical part, lead acid batteries, all these batteries, classifying the lead acid batteries, the advanced lead acid, all these zinc batteries, etc., sodium batteries, etc. Now the thermal system, the thermal classification level, from we can see latent storage, the phase change materials, thermochemical storage, etc. From the electrical perspective, we can observe that supercapacitors, superconducting magnetic energy storage systems, and from the chemical or the hydrogen fuel cell. So you can observe the hydrogen fuel cell, and this is mainly the classification which is this is from the reference of NITI Aayog, niti.gov. So this is the Indian energy roadmap, which is the predicted roadmap of the energy storage in India in the year 2000 by 2027. So previously also I've discussed that the present the present day Indian scenario. So what we can observe is that the generation by 2030, the renewable energy generation should be around 20, feeding around 50% of the total net demand. So if we are to feed 50% of the load demand by 20, so this is a kind of ambitious improvement, ambitious goal that has been fixed, but might be achievable. So we can observe and see. So this is also a kind of roadmap by India as proposed in this reference by 2027. So we can observe that the here we have the rooftop solar generation for each and every places, and the total energy storage in megawatt and megawatt hour. So these are the places. So these are nothing to discuss much in this. So this is the data, and we can observe that it is being significantly India is trying to significantly improve in this domain. So So from the power systems perspective, we what stands the need of these of the energy storage system, so that we need to understand and discuss already being discussed. So it's a kind of overview that so what we have to do is to maintain the frequency, and we have to the flexible ramping of the generation and black start services. So here we can observe that the for the frequency regulation, the ESS means the energy storage systems allows this see for the system operation point of view, the frequency regulation, the flexible ramping, the load duct curve is written here. So what is load duct curve? We will be discussing later. Means yes. So for the black start services from the power restoration. So suddenly when we have to restore the power, the transients of the system needs to be observed, needs to be fed. So in those cases, the renewables can't feed those sudden black start services. So in those cases, these energy storage devices, energy storage systems can provide the essential services. And from the investment deferral point of view, so since the transmission systems are quite transmissions are quite well developed, so presently to cater the load to some places where the demand is high, so in those cases what we are trying to do is to we can place the energy we can place these battery energy storage devices in those areas, and based on that we can perform this the energy shifting can be made, and the transmission system balance means that we don't need to suddenly improve the entire transmission architecture. So this is the advantage. So if we can install these storage devices at those locations, so in those cases the energy shifting is not means energy shifting takes place, but the transmission system stays as it is. We can means the congestion of the transmission system can also be leveled down, because if suppose we place the or install the battery energy storage systems to those places, so in those cases the load demand would be met in the locally in those areas. All right. And from the PV or wind generation or mini grid point of view, so The reduced energy curtailment means since we have the battery energy storage system, so in these battery energy storage systems can we have the renewable power injection all throughout the day. Means for the wind it is all throughout the day if there is a wind flowing. And for the solar we can have the solar power generation all throughout the day during the daylight hours. So what it is observed that the renewable energy has to be maintained in a proper manner, because if the is demand is somewhat to some extent we have to meet the demand anyhow. So if the demand has to be met from the point of view of the generating units or the operations of the operations power system operations point of view, so the renewable energy is an uncontrollable part. So how much they are feeding, we need to absorb or we need to deliver the load to the system. So in such a case, the battery energy storage is a good choice, because if we have higher amount of generation from the renewables, so we can store the energy that amount of energy in the form of battery energy storage, and whenever it is required we can directly feed to the grid whenever it is required. So this is the advantage when that is being provided by the RE, means the renewable energy curtailment and capacity farming. And we can also reduce the reduce the reliance on the diesel generator. So our reliance on these diesel generating units we can regulate, because they are these diesel generators do emit the carbon to the system and the greenhouse gases into the system. So we need to regulate the use of these diesel generators. And one such option is to have this battery energy storage system. Right? So so these are mainly the classification, means the energy storage system point of view. If we try to from the utility point of view or the energy storage point of view, what are the features or what functioning do aid the proper operation of the grid if in the presence of the energy storage system. So first of all we can maintain the frequency. So if suppose we have to maintain the frequency anyhow, means we'll have to plus minus 5%. It is being generally not at all 5%, means it's a huge change in frequency. So we generally it is being tried to maintain from 49.5 to 50.5, means 49.85 to 50.05 and something like that. So it is being maintained tried to maintain within that range. So if such a frequency regulation, and for that if the generating units can maintain such a frequency, then for that they get added benefits from the tariff point of view. So frequency regulation in our Indian context is a must. So frequency regulation is, and how to maintain the frequency to deliver the required amount of power. In the sudden rise in frequency happens if the load is sudden rise in frequency happens when the load is less than demand. If sudden drop in the load, and for the load higher than demand, the frequency frequency falls, and here the frequency rises, and here the rises load rises, frequency drops, and frequency load drops, frequency rises. So frequency regulation, then the grid investment deferral. So grid investment deferral from the transmission system point of view, if somehow it is being the location of these energy storage systems can be made to such places where we have the grid investments. So the transmission system need to, if suppose in a load center is far away located from this generating units, and which is a quite apt case. So In such a scenario, the grid investment has to be made because of the transmission system to relocate to transfer the power from the generating stations to the transmission system to the distribution to the location of the load center. So in such a case, so we need the transmission cost, and these transmission cost is quite high. So right of way and all these things needs to be first addressed, and this right of way has to be in the mainly the kilometers are quite 200 300 kilometers long transmission lines. So what we can do is that if we try to develop the energy storage, generating energy storage devices, if we try to establish an energy storage systems in the area where in the load center itself, so we can save the grid investment from the transmission point of view, and congestion can also be reduced, and the reduced renewable energy curtailment. It is also what I've discussed before, that renewable energy curtailment is a part of the means. Suppose we have the generation the solar generation all throughout the daylight, and the wind energy generation if we have the wind. So what we need to is if in the absence of these energy storage devices, so what we can do is to regulate the amount of wind generation or the solar generation if required, if there is no storage devices placed in the system. So and why it is needed, to at least to maintain the demand we need to maintain the frequency, and the generation has to be meeting the load as well as the losses. But if the but these renewable energy generation units are uncontrolled, so whatever they generate they have to be utilized. So in wind energy storage systems, we sometimes we control the blades of the wind turbines wind the blades of the wind generators wind turbines. So by varying the pitch angle we can try to we can means varying the pitch angle we try to control the generation. So this is not the case if we try to if we have these renewable energy these battery energy storage systems in our in our in our power system context, and the reliance on diesel generators, mini grids, all these things. So being discussed. So India's battery storage system scenario is that currently India has 37 megawatt of battery energy storage system, and from its power it requires 236 gigawatt of battery storage gigawatt hours and 230 gigawatt hours of battery energy storage to addition of 27 of pump storage systems. So mainly the pump storage systems are quite a huge these pump storage systems in West Bengal. Also we have the uh, around 250 megawatts, 220, yes, 900 megawatt. It's Purulia pump storage project. So it is being maintained by WBSCDCL and ACDCL. It has around 900 megawatt generating capacity with 225 into 4 generators feeding, and during the off peak hours, so it is being maintained by WACDCL. During the it has a generation capacity of 900 megawatt with 225 megawatt capacity of each unit, and there are 4 units. And during the off-peak periods, when the water is being pumped from the lower dam to upper dam, it requires around 250 megawatt of the power, 250 megawatt from the grid. It requires power from the grid, and hence to maintain the grid stabilization, or to maintain the grid to be grid frequency as a constant. Okay, so this is, and another also, the another pump storage is being established. It is called Turga pump storage. Turga pump storage, it is also maintained by WBSCTCL. So it has the generating capacity of 1000 megawatt with 250 megawatt of 4 units. So these mechanical energy devices do aid in maintaining the grid frequency. These are also, and these are mainly the mechanical energy storage devices. So this is the first part. So coming to the various types of energy storage devices. So we have the mechanical pumped hydro compressed air flywheel, the electromechanical. This is from the lecture itself. The lithium ion, the battery electrochemical, and then we have the chemical fuel cell, hydrogen fuel cell. Then we have electromagnetic supercapacitor, superconducting magnetic energy storage system. Then from the thermal point of view, latent heat, sensible heat, and hybrid system. So in hybrid system, we can make the merge. We can merge any two of the system and make a separate kind of system, which is again applicable in a better fashion as per the demand requirement. Means suppose we require to the electric vehicles also, hybrid electric vehicles are being present where we have two kind of energy energy delivering devices. So most of the, this is types. These are mainly the types of the energy storage devices. Now coming to the terminologies. So first of all, energy density. So what we can observe is that energy density is the amount of, means we need to deliver that much amount of energy which is being stored as per the given volume or mass. Okay, so it is the amount of energy which can be stored in a device for a given volume or mass. And similar kind is the power density, and here we mainly consider the power aspect, and this much amount of power that can be stored in the devices. This is the power density, and the response time is that this is the response time. What it is from 0 to 100. If we need to rise from 0 to 100% of the rated power, then rated power divided by the response time. The rated power by the response time will be giving the ramp rate of the system. Ramp rate of the system. Again, it is the cycle life. So how many times the cycle life, the energy storage system can be used? This is the cycle life. What is the lifetime of of the storage devices? And efficiency is the efficiency that has to be maintained. Is the after the energy that can means, suppose the input means to charge a battery, we require some amount of energy, and what is the output that can be taken, input by output, output by input. So this could be into 100. This would be giving the energy percentage of the system. So some applications of the battery energy storage system. So BSS battery energy storage prospects. So again, the transmission and distribution upgrade different. So we don't need to upgrade the transmission and distribution system of the distribution system, because if we can place these in a battery energy storage system to the locations where the to the locations of the grid or the load or the demand centers. So in those cases, what we can find out is that the transmission and distribution costs can be deferred. The voltage regulation. So voltage regulation, we have to maintain the voltage, and for that is the sending end voltage and the receiving end voltage. we have to maintain the, say, receiving end voltage to a certain level so that the percentage voltage drop doesn't exceed the specified limits. So for that we need to persistently maintain the voltage at the receiving end, and hence the voltage regulation. So these, and this is the advantage which can be given from this advantage means from the battery is energy storage or the battery energy storage point of view. They also try to allow, they also deliver the voltage means to maintain the proper voltage regulation to a minimal level. And coming to the frequency control, so this is the frequency. We need to match the frequency of the system with the means we maintain the frequency of the system all throughout. And to maintain the frequency of the system, what we can do is that we need to maintain the generation and load balance. So again, this energy storage system can aid in the frequency control and the ramp rate. So suppose in the from the black start point of view, so we don't have the, from the black start point of view, we don't have that much amount of resources from the renewable energy side. From the thermal side, we do have, but it requires means the commitment should be entirely made proper unit commitment, so that during this ramping ramp rate or the from the black start the sudden ramp, we can means during if sudden load changes or this kind of scenarios occur, we need to commit all and each and every generators or each and every generators to the system. So so as to maintain the sudden spike or the ramp or the initial transient period of the load or of the load generation balance. So what we can do is that during those time commit the battery energy storage so that the ramp rate can be maintained, also as to maintain the ramp rate to a certain level. And the commitment of the generators, because we have presently, due to the uncertain nature of the grid, the uncertainty of the grid is quite high. Means previously what we had is that we generally had the amount of generation was mainly means from the conventional point of view. So when we had the amount of generation, and this generation from the thermal mainly, which is controllable thermal or these thermal power plants, the conventional. So during those times, so the entire control was on the operators. The operators had the full control, so they can control as per their need. They can commit that amount of generator or that amount of generator to the system, so that the load can be met. And load forecasting was a common phenomenon. So to meet the load forecasted load, the thermal energy, not the storage, sorry, the thermal power plants can directly feed. And the uncertainty level, this was the main point why the battery energy storage system is aiding the Indian or the entire global scenario. The uncertainty level was around 5 to 6%. Means this much amount of spinning reserve we had to keep in the system so as to maintain the frequency constant, because the forecasts were not uncertain, they were uncertain up to 5 to 6%. And for that we can only, they only keep this 5 to 6% of spinning reserve in the system so that they can deliver the remaining amount of, means the 5 to 6% would be delivering the sudden any kind of abrupt changes and all these things, the uncertainty of the forecast. So but in the present scenario, where we don't have the, we have the uncertainty of the renewable energy storage system. Renewable energies uh, are around 15 to 20%. So for that we also need to commit 15 to 20% of the generation of the from, and that too also with the help of the, that too also with the help of these um, thermal, means the spinning reserve, to spinning reserve. since the inertia of the system is getting reduced, the system inertia is getting reduced because due to the lesser and lesser amount of thermal energy, thermal plants being feeding the load, and by 2070 as government has proposed to net zero, means to deliver the entire load by the renewables itself. So the grid inertia is gradually decreasing, and with the decrease in grid inertia, the problem is that the the uncertain behavior, means due to the uncertainty of the renewables, these due to the uncertain behavior of the renewables, the there it cannot demand, it cannot meet the sudden variations, and for that we need to commit more and more generators, more and more thermal or the rotating masses in the system, and sometimes the flywheel mechanisms also do play a part, flywheel mechanisms. So this is the main scenario of the why, what is the main advantages of using battery energy storage systems. So coming to the duck curve. So what is the necessity, or what is the real-time interpretation of the duck curve? Is the duck curve shows that during this, from starting from the 6 a.m., from 6 a.m. when the sun rises and till the 6 p.m. when the sun sets. So during this span, what we can observe is that the load curve is gradually decreasing. So is the load gradually decreasing? So if the question comes is that is the load gradually decreasing in between this period? So the answer is no, because the load is not gradually decreasing during this entire period of time or this span of time. What the thing is happening is what the thing happening due to the due to the due to the sun or the solar energy, due to the solar generation, which is a renewable form of energy, and around 16 to 20% of the in the 16 to 18% or 20%, we can also tell around 20%, not 20% exactly, less than 20%. This much amount of less than 20%, but more than 16%. This much amount of generation. So it's a quite significant, as India's demand is around 410 gigawatt. So to meet the 410 gigawatt, if around 20% of the generation is coming from the solar solar energy system. So what we can observe is that during these from 6 a.m. to 6 p.m. the load curve falls, and in general we have the two peaks. This is the in general load curve, and where we have the morning peak and the evening peak. But here what we can observe is that as the renewables are the solar energy is generating more and more during this period, and it's when the sun is at its highest, sun is at its highest irradiance, of the sun, the load curve falls significantly. So what we can observe is that this much amount of sudden fall and rise in the load curve is creating a troublesome situation in the entire power grid concept. So what we can do is that during this period we can deliver this is the main, this is the ramp, this is the sudden increase, this is the increment in the power. So during this increment period, means the slope is in rising slope. So what we can do is that we can feed the power from the battery energy storage systems so that battery energy storage system can feed these power means during these times, so that the ramping rate and all these things what I've discussed previously, that during this ramp period these battery and this storage system can provide sufficient amount of ramping criteria or the ramping observation, or they have this amount of ramping kind of what we can say, they have this ramping feature, so they can deliver this amount of ramp to the system, and hence the frequency, and ultimately we have to maintain the frequency of the system constant. So they can do this kind of take part in this duck curve, and hence the main agenda is to deliver the load. We have these two features, that is peak shaving and valley filling, and this is the peak shaving and valley filling. This is the valley, so we need to incorporate more and more energy storage system. We can means the transfer the loading. This is the peaks. These peaks, this we can transfer the loading from the peak to the off peak hours, so that the entire load curve is tried to maintain flat. Although this kind of straight nature of the load curve can't be maintained, but at least these peak hours can be lowered down to the off peak time, so that the peak shaving happens. And this kind of things happen with the in the smart grid environment, where the customers do take part in the demand response program, in the demand response program, and all these and demand response program. Yes, when the incentive customers are incentivized with based on their consumption, means during this government or the utility companies do provide this kind of information with the help of the communication medium, that if the customers can if the customers don't use or reduce their the we have mainly loads are mainly classified as luxurious load and essential commodities. So they can maintain the essential commodities and the luxurious commodities. So luxurious commodities. So if they can minimize the use of the luxurious commodities during these off peak hours, so then the demand response architecture can take a proper place, and hence these peak shaving and value filling point of view, and hence thereby maintaining the load curve to be a flat profile. Although this flat profile can be maintained, but still it can be made flatter. Okay, so this is the main observation from the duck curve and the peak shaving value filling architecture. Coming to the battery storage architecture. What we can see is that, so any kind of, so this is the battery energy storage system. This is the model, means this is a kind of model or representation of the battery energy storage system. Okay, so what we observe is that this is the ideal storage, and these are the charging and discharging losses of the system. This is we have the three states: charging, discharging, and idle condition, ideal operating condition. And during the idle conditions, there are some losses taking place. Then we have the AC or DC losses, and the rest they are fitting to the grid. This is the main operation of the battery energy storage system. So this is the ideal storage system. So what do we mean by ideal storage system? So it will be generally lossless in nature, and the ideal energy storage system would be lossless. in nature, and the and it would be delivering the net demand. And this is the lossless system can be in a practical scenario, there can be lossless system. So but still, yes, it is considered lossless because the losses are considered later on. So after the ideal energy storage system, we have the charging and discharging losses. Here we can see charging losses, charging and discharging losses. Okay, and this is mainly with the associated with the conversion from the storage medium to electrical energy. Means we can be convert from the storage medium to electrical energy. The amount of losses that can be considered as a charging or discharging losses, it is this case, the charging and discharging losses. Next we have the idling losses. So what are idling? We suppose that the battery is kept for a long time, is kept idle for a long time. So idle for a long time, and in those cases the it is a kind of the battery depletes, means battery self it is a kind of self depletion of the system, self depletion of the energy. And and due to the presence of auxiliary loads in the system, so these are the losses which is being paid by the losses which takes place as a part of idling losses. And then we have the AC and DC inverter losses. So the switching losses, mainly inverter. So these are switched on and off, and based on their switching times, the switching losses takes place. And also the inverters, they do not only inverters. Yes, this one. This is the grid bus system where we are feeding the towards the grid. And these losses mainly are dependent on the ratings of the devices. So these are mainly based on the ratings of the devices. Okay. So this is the operating model of the battery energy storage system. And yes, so so let us. This is the final equivalent model of the system. So equivalent model of the system representation, where we have this is a dependent voltage source and the self discharge resistance. Then we have the capacitor, the R1 and R2. We can model it in a more number of R and C circuits in parallel, but here R1 and up to Rn is shown. So the more number of R and N blocks can be added into the system, the more accurate the transient behavior can be observed from the system, and hence this is the equivalent model. So so we can write the energy stored. This is the energy equation. The energy stored at a time t is given by del t times the discharge by the efficiency of the system. mm, Efficiency. So this is the main operating equation. So we have this kind of constraints where the charging plus the discharging should be less than equal to 1, and also the we can't discharge the battery to the zero position. So what we call is that the depth of discharge. So we can't directly make the battery discharge to to 0%. So we have to maintain a specified limit, because if we do the same, then the life of the battery decreases. The cycle life of the battery decreases. So it is called the depth of discharge. So we need to maintain a certain level. So this is the this is the energy stored at time t, and this is the constant that we need to follow at any point of time. The charging and discharging rate should be less than 1. So yes, now comes the SOC. SOC and DOD, state of charge and depth of discharge. So by the state of charge, we mean that the amount of charge which is present in the battery, and the depth of discharge is how much the battery has been discharged. So it is clear from the figure that it is 100% SOC and 0% DOD. Then we have this is as 20% SOC, means 20% of the charge reduction, and 20% of the charge is present. Sorry, 20% of the charge is present, and 80% is DOD. But it means that 20% energy is left, so we need to maintain this amount of energy so that the life of the battery is maintained or held constant. So this is another possible diagram. So here we can observe that 65% of the charge is left, and DOD is 35%. Okay, and this is 0 SSC, entire is discharged, or 100% DOD. So SOC and DOD are related as 1 minus, means 100% minus, or 1 minus DOD, or 100 minus DOD, in such a fashion. If we consider is an SOC percentage, then we'll have to consider as DOD percentage, and this is 100%. So it's a question that why is it very low DOD not recommended for a battery? Because if we constantly decrease if we discharge the battery up to a certain level, if we constantly discharge the battery and on a regular basis up to a limit, means suppose we have to maintain, means the manufacturer specifies the limit as suppose 20%. So if you don't maintain the if you don't maintain the 20% limit, and we suppose for our mobiles and all these things, what we can observe is that the each and every time when it goes to less than 20%, it is recommended that one should charge the battery and don't allow the battery to go beyond this, go less than 20%, because in those cases the parts of the batteries, the electrodes and all these, they degrades, and due to which the life cycle of the battery reduces, and hence it is not recommended for the battery to go beyond a certain DOD level. Has to DOD is fixed. The manufacturers fix the DODs for the customers. So mainly battery aging also takes place, and hence so we have the number of we have the one of these is the cycle aging, battery aging, battery aging. It is mainly depend upon the time, the time, temperature, temperature, DOD. etc. And what we have, one thing is the another thing is calendar aging. This is calendar aging where we can observe that it is a matter of time again, because time the entire variation is based on time. And again we have the temperature, and we have time and temperature, and the associated state of charge. So, and one thing is ESS lifetime, means energy storage system lifetime. So we can relate the energy storage system lifetime as 1 by battery degradation. 1 by degradation. And what is degradation? Degradation is number of cycle and total number of cycles to failure. The number of cycles performed for the DOT, and total number of cycles given performed. Yes. So this gives the energy cycle, energy storage system lifetime. So, so in the equivalent model again, these self-discharge means, again this self-discharge context, that's when the battery energy storage systems are being kept for a long period of time. So during those situations the batteries discharge, and this self-discharge is being represented in the model as the resistance as a resistance. And this is the open circuit voltage, and these are the resistances and reactances or the capacitances of the system. And I previously told that to capture the transients of the system in a proper manner, these are model means if we incorporate more and more number of the resistance and capacitances, then we would be obtaining better responses of the transient behavior of the system. So this is the SOC DOD, state of charge and depth of discharge. So how they are related, so we have discussed. So the main other thing is that the entire distribution system is the entire study of the smart grid is mostly focused in the distribution system itself, because as we are trying to keep or trying to invest more to the energy storage system or the various kind of generation or the renewable generation. So all these conditions are being or these conditions are dealing with the distribution, because the most of the important thing is that the transmission system is quite saturated, means saturated in the sense that we need to invest, means we need to create transmission system expansion. This expansion needs to be done transmission system, so or because their load is gradually increasing day by day, demand is increasing, but the that amount of overloading capacity, if suppose the transmission lines have to have their limitation of the line overload. So what the people are doing is that to restrict the transmission level, they are mainly emphasizing on the distribution level. So generation and all these things, the renewable generation are mainly taking part in the distribution level, and hence the distribution system are also known as active distribution networks, because the distribution systems are quite active because they have the sources at ADNs. So they have the sources. They have the sources like solar, wind. Now coming to the storage, these storage systems are also kind of generation sources. So proper siting, optimal location and sizing, location and sizing needs to be performed. Optimal location and sizing, and since the optimal location and sizing would be leading to a proper allocation, so that the distribution system, another thing is that it is mainly radial in nature and weakly meshed in some cases. So most of the general distribution systems are radial in nature, because the main purpose of keeping the distribution system as radial, because they have the protection system, the distribution system, the protection system used in distribution areas, the protective equipments needs to be improved further to incorporate easier protection system needs to be improved. So easier protect distribution system protection are there. So equipments are easier and they have to respond fast. So what is being generally performed is that it's a radial type of system that is generally maintained, where the loads are being catered from each and every buses, and these line drops. And so we if we have to place the DGs, the DG allocation, so if we have to place DG in suppose a place, so the optimal sizing and the optimal allocation is a must. So in the optimal DG allocation problem, it is generally considered that DG is a special, is a general practice. General practice is that we allocate the DG in the places where it is the weakest uh, voltage buses with the weakest voltage levels. So in this manner, they from the weakest to the weakest voltage levels. So one by one, if from starting from the most weakest, means the weakest bus, not most weak, so weakest bus to weaker, and this gradually improves. So first DG allocation will be DG will be placed at the weakest voltage level buses, then increasing in a gradual increasing manner. So this is the general practice, but people might consider the other cases. So for the optimization problem, it is generally chosen to be the weakest bus, and mainly the this is the optimal choice, optimal allocation or siting, and then we optimize the size of the DG, because in some cases what we observe is that whenever we are optimizing the DGs to level to an extent, so we generally perform the test cases scenario if in our mainly in our laboratory or in our various kind of softwares. What we do is that we generally perform the we run the load flows, and the distribution load flow is generally forward backward sweep load flow is performed, and here the optimal we perform the various kind of how much amount of DG placement is necessary. So in some cases 50, 40, and all these things are tested, means 20, 30, And what we observe is that suppose we find that between 40 to 50% of the net demand means we can allocate the DG here. Between the DG size location is fixed based on the weakest bus, and from the weakest after the weakest bus is placed, when the DG is placed at the weakest bus, then optimal sizing. So suppose we obtain that in between these 40 and 50% of the total generation, we find the optimal place. So suppose in a such a context that up to 40, from 10, 20, 30, and 40, suppose from 10% of the DG, then 20% of the, then 30%, then 40%, then 50%. So up to 10, 20, 30, the there is a voltage improvement. So what we can observe is that the voltage, previously if the voltage is like this, maybe in generally it may be a case. So it is a general case. We can consider that for the distribution system. So this can be a profile. So what we can observe is that this there has to be some improvement in the voltage profile. So people are investing more to get at least a better voltage profile. So this amount of improvement is made, has to be made. So we can minimize the losses, the system losses can be minimized, and also the system, mainly the system losses are to be minimized, and voltages are to be maintained at their within their limits. Means the 5 to 6% deviations of the voltage is allowable, but beyond that it is not allowed. So this much amount of improvement in the, this much improvement. So what we observe is that after running the optimization problem, we would be obtaining a proper location somehow around 37%. So what we observe that if we go beyond 37%, again the system voltage profile violates the means the voltage limits, that is the 5 to 6% of deviations than the steady state voltage. So hence we perform the optimization, which can be mainly done in mathematical optimization, meta-heuristic. Generally, nowadays there is a common trend of utilizing the meta-heuristic approaches in the optimization problems, artificial intelligence techniques. So what we can observe is that this being an energy storage system which can be compared as a generating unit, the this can be treated as a source, and this source is delivering or meeting some demand, and this demand, this is placed in some distribution system. So optimal allocation and optimal sizing has to be met. And there are some network information, means the input will be network information, and the cost parameters and the ESS, and output would be optimal operation and serving for the chosen application. Okay. So based on that, the objective function can be kept as minimizing the investment of the system, or minimizing the operating cost of the system, or minimizing the operating cost of the system, and or minimizing power loss, or minimizing voltage deviations. Any of these can be kept, or it can be multi-objective function based approach. And here we have the constraints of power flow, means the power flow limit has to be met, the current overloading capacity has to be met, and the our upper and lower bound. So for this purpose, we mainly go for the meta heuristic applications, and sometimes there it forms the mixed integer linear non-linear MINLP, mixed integer non-linear programming type operation. And after the proper output, so what we can do is that validate in the test system. We have done it in the test system. Now we then try to implement in the practical system. Okay, so for this energy storage system optimization, it is generally considered that the each and every mathematical result, these are each and every mathematical method, means the meta heuristic or mathematical optimization, artificial intelligence, each and every method has their own advantages and disadvantages. Like to reach the global minima, means the losses are to be minimized. We have we have to, it is a compute means we can it is a, maybe a computationally burdensome approach. Like we have many optimization techniques, and each and every optimization technique is better than the other in some context and can be comparable in some context and can perform lower means from the point of accuracy or point of means optimization level of the reaching the global optima. Sometimes it gets fixed to the local optima, and then such this operation means the global optima is not reached. So these are the issues sometimes with the system. So one such test has been performed in the lab, and that has been discussed by Professor N.P. sir. So these are mainly the approach, the optimization approach, and yes, these are the mainly optimal. So not much to discuss in the optimal allocation. So the constants are to be kept as the discharge of the charge and discharge rate of the system, the UCH and UCH plus UDCH should be less than 1, or UDCH should be less than 1, and the the initial and the initial and the final. This is the final, and this is the initial. Should not reduce to 50%, should be more than kept with more than 50% of the generation, means 50% of the battery energy should be present. And these are the main objective function, and these are the constants that need to be developed or that need to be met for the performing the optimization problem. So we would be finding the ultimately the voltage profile of the system, and based on the voltage profile we can be calculating the errors previously, and with the error from the previous operating scenario to the with the next, and hence we would be obtaining some optimal best size and site of the energy storage system. Okay. So what we can see is that, so if we can optimal choice of sizing and allocation. So again, for the transmission system, since the transmission system deferral was being discussed previously, cost deferral, and hence in these cases, if we can properly find the exact load center, run the optimization in the distribution system, and hence we would be obtaining the optimal place so that the distribution system cost gets reduced, distribution system expansion. And suppose we have the if there are the uncertainty of the renewables, this uncertainty of the renewables, So in those cases, the battery energy storage system would be aiding the operation, and hence what we can do is that we can consider the battery energy storage system the uncertainty of the renewables, means to deal with the uncertainty of the storage system we can consider this as a constraint, or the as we can deal with this can be as a part of the constraint, the uncertainty, the objective function can be modified with the constraint so that this can be treated as a part of BSS, is the optimal sizing and allocation. Okay, so this is the main part, and this is coming to the choice of the battery. So what we can observe is that choice of the battery, the as per the application point of view, we have the choice of the battery is quite critical. So we can observe lithium ion in IMH, nickel cadmium, and lead acid battery. So we can observe that based on each and every the specific density, so we can observe that the as we go from the if the volumetric energy density increases, which is high for the lithium ion, so in those case the size of the battery will be smaller, means in small place, small area or small volume you can concentrate the battery so that the volumetric energy density is met, and again the specific energy density. So based on this purpose, so as we go towards the end, so we observe that the it is lighter in weight also. So lithium ion battery is the best amongst all the energy storage system, but the cost of lithium ion battery is also quite high, and hence these are there has to be a trade-off between what is the need of, means where to implement the lithium ion battery and where to implement or to use the lead acid batteries. So there are some there are we have the lithium ion battery in our mobile phones, the storage devices or the electric vehicles where we have to properly utilize the system or the energy or the storage in a stored energy. So in those cases, we try to use the lithium, and as the cost of the vehicle or the cost of the mobile phones and all these things, we can increase, and the is they can increase because the candidates or the person who are buying these equipments, they can at least invest more to get the better life cycle of the system. So owing to this scenario, the lithium ion battery, these are some of the applications where we can find the telecommunications areas, the PV generation, storage, the tools with the electric vehicles, etc., etc. So we can see that UPS, bike, etc. We can see that the lithium-ion battery is used. So these are mainly the application. But suppose from the is what from the means the areas where the people can't invest more. So in those cases, the lead acid batteries where the daily life activities are to be met, and to meet those daily life activities, the people use the lead acid batteries, which are cheaper in comparison to the lithium ion battery. Although this with the increase in the specific density and volumetric energy density, lithium ion battery is delivering the is the best suited result for our system to use for the system. So, so coming to the battery management system. So, what is the battery management system and why it is needed? So that we need to understand first that what is battery management system, that it is a kind of it is a top layer that is being added with the battery, and this is the battery management system del- delivers the instructions or directions in which the the entire battery packs or the battery banks would be performing or delivering the charges to the system, or will be charging as per the instruction or the or the information or the code that is being or the operation that is being particularly designed in the battery management system. So to get the optimal output and the optimal result for the operation of the battery, so the battery has to there are to be some information which should be fed to the battery management system. So these are the measurements with like the voltage, temperature, and current. So we using these information, so SOC estimation is a prior objective that is being maintained. So SOC estimation will be delivering some detailed output of the operation, and hence we need to have the proper SOC value, and without this proper SOC value we can't even operate, means we can't even know, means whether we are buying an electric vehicle, and based on that electric vehicle, if we don't have the proper monitoring equipment, then the cost or the investment that is being given or that is associated with the electric vehicle will be in vain. So this battery management system is quite an important architecture, and it generally, this is the voltage measurement, temperature measurement, current measurement, and it gives an optimal, means optimal operation of the battery is established. Operation of the battery, optimal operation of the battery is established. So with the optimal operation, what we can do is that the proper functioning can be maintained, right? So SOC estimation is a very wide area of research, and it is quite dominant now till date also, where people work on the various conventional techniques and adaptive Kalman filtering techniques, some data-driven approaches, deep learning approaches, etc. So here mainly the state of charge estimation is performed with the informative model of the system, where the conventional model is quite simple enough. So sometimes let's first discuss the basics of the machine learning, the data driven approaches, where the we have the data, means the previous data and all these things, and based on that we use the various classification techniques and try to implement it so that the output of the SOC estimation is proper. And this requires an online monitoring. First of all, it requires online monitoring of the SOC, because if we can online monitor the system, means the SOC online, then only we can have the, means the strict idea of the how and what is the present operating scenario of the battery, right? So like the adaptive Kalman filtering techniques, so Kalman filtering techniques are mainly the nonlinear approaches, are mainly this application of Kalman filtering in SOC estimation is quite old, means so people are trying to develop adaptive algorithms, because the information that we generally obtain from the Kalman field for the as a measurements, this voltage, temperature, and current, these are the measurements. These measurements will be giving these measurements that would be fed to the Kalman filter is is of noisy data, this kind of noisy data. So we need to estimate, because we can't use the term the proper, we can't find the proper value of the system, so we would be using the term estimate. So that's why it is SOC estimation, because based on some noisy data, based on some erroneous data, we need to find the near possible operating states of the system. So like in the nonlinear Kalman filtering, it is kind of we have the various Kalman filtering techniques like extended Kalman filter, like unscented Kalman filter, the then we have cubature Kalman filter, and all these things, and cubature quadrature Kalman filter, etc. So these are some of the basic Kalman filters which are non-linear in nature. linear Kalman filter won't work because the measurements that are being obtained are, or rather they bear the non-linear behavior or non-linear nature with respect to the input state variables. So now, to make this system robust and the adaptive in nature, where we don't have the information of the variation on how the measurement noise are being generated, means measurement noise, we don't have the information on how the measurement noises do vary. So based on that, the adaptive techniques are techniques are being implemented in SOC estimation. These are recent trends. Adaptive nonlinear Kalman filtering approach or implementation is quite old, and deep learning is also a recent trend where we can use these various kind of LSTM approach, long short term memory approach. Here is a part of a recurrent neural network. So these kind of deep learning approaches are being implemented recently, and lot of publications are being generated based on this application of the data driven approaches as well as the adaptive Kalman filtering approaches. So to discard the noisy data in the Kalman filtering approach, the this kind of estimation is being performed, and the behavior of the noise can vary at times, and hence the also the randomization can be Gaussian, non-Gaussian, etc. So these are some of the techniques with for the online, and the SOC has to be monitored online. So prior prior setting up these kind of or implementation in a practical scenario, these are done in the in a closed loop spaces, and then the in the software environment, and then it is implemented hardware in the hardware so that it is in properly, and this BMS has this kind of features inbuilt in it, so this aids in proper monitoring of the system or the SOC estimation of the system. So now comes the cell balancing. So using with the cell balancing, we can observe that there are a large number of cells connected in series parallel combination. So what we can do is that the series parallel combination of the cells. So each and every cell has to be maintained at a and the same amount of energy should be present in each of these cells. But in practical case, there are some deficit, means some cells do discharge fast and some cells do not discharge fast. So if this should be the condition that I have drawn, and based on that the based on the discharging rate. So if these unbalanced cells, means this is the general case. So this is the discharging direction, this is the charging direction. So if the unbalanced cells get discharged, the final outcome is also a discharge. The final, this is the final after discharge. So that is also in a condition where uneven charge is being left in the cell. So after if I remove these plots, these markings, so you can observe that the there are some uneven pattern in the discharge, and similar is the condition when these unbalanced cells are being charged, then each and then again there is unevenness in the system. So to maintain or to deliver the proper outcome, means the proper outcome of the system should be maintained to utilize each and every cell to its ultimatum, to its highest level. So what we can do is that we can use the we can perform the cell balancing, and based on the cell balancing which can be done in as an active cell balancing or passive cell balancing. So generally active cell balancing is in practice, and we have various kind of techniques being discussed, but in the passive cell balancing we just use some resistive networks to just balance the cell, to perform the cell balancing and control them. But in active cell balancing, there are many approaches that are generally performed with the single tiered switch capacitor and the single with the single tier switch capacitor with the double tier switch capacitor, and these are some of the approaches. So mainly some power electronics implementation are being performed for these cell balancing techniques, the flyback converter types and all these things. So that these are the active cell balancing, and with the help of cell balancing what we can do is that to maintain all the energy stored in the cells to a certain level so that they discharge or charge at the same rate and the lifespan of the cells are being held constant towards the end. So this is the overall architecture or overall analysis of how cell balancing are being performed. So there are some cell balancing techniques, and so this is the main operation of the cell balancing techniques. How the battery management system performs and cell balancing happens. So let's have some basic discussion. If you have any queries, then we can discuss, and otherwise I have some MCQ questions that are prepared from the previous year, previous term's lecture, this previous year lecture, I think in the last semester itself only. So we can discuss. So and you can write it in the chat box also. So I think it is visible, right? Which of the following is not a type of mechanical energy storage system? Latent. Anything more? Two. Okay, two and D. Mechanical, not a type. So please, not a type of mechanical energy storage system. So yes. So it is four. It is latent. Latent is the right answer, and not two. So I think this question is also visible. Which of the following combinations of energy storage technologies are not feasible for hybrid energy storage system? 2C. Okay, anything more? 4. So 2, 3 and 4. Three answers will end. So anyone is correct out of these. One of the answers out of these three is correct. On three of them can't be correct. So So, so the answer is none of these is correct because these all these three combinations like supercapacitor, battery, lithium ion and sodium sulfur batteries, vanadium fluent lithium ion batteries, all these are possible hybrid energy storage systems. So since it was even not feasible, so all these are feasible. All these three are feasible. So okay, let's. So here we have a match kind of thing. So chemical, mechanical, electrochemical, electromagnetic, flywheel, battery, fuel cells for conducting magnetic energy storage. Answer C. What is C means A3? A3 chemical is fuel cell. Electromagnetic chemical is flywheel. Flywheel is B1. It's okay. C. A is 3 chemical fuel cell B1. Electrochemical is CV2 and D will be B. Yes, answer is C. So A is chemical is fuel cell, mechanical is flywheel, and electrochemical is battery, and the electromagnetic is the superconducting magnetic energy storage. Following the high energy density, so high energy density is yes, it is lithium ion cell. Then 12-volt battery with the capacity of 5,500 ampere hour is at 80% SOC. So what will be the DOD depth of discharge? All are 4 means 20. So a 12-volt battery with a capacity of 500 ampere hour is at 80% SOC. What will be the energy stored? Energy stored. So 80% means 80 by 100 into 500. So that would be 400 ampere hour. So this much amount of charge is left. So this would be SOC. The amount of energy stored is indicated by SOC. So 400 is the correct answer. So which type of problem is a distribution network planning problem? Distribution network, so planning problem with the objective function constraints that I've discussed previously. So it is a nonlinear problem, and this can be performed using it is a MINLP, mixed integer nonlinear programming. So answer 3. Mathematical programming approach advantage. Select the advantage of the mathematical programming approach. Low computational burden, global optimal solution, short convergence time, simple formulation. Mathematical problem programming approach all is not not the right answer because it's not a simple formulation, and, and convergence time is also not the correct answer. If convergence time was given as an answer, I can see C as the answer, some of the answers. Maybe of the previous one. But for this one, the mathematical programming approach, only one answer is correct in these four options. Out of these four options, C. C. Anything else? Somebody else? Yeah. C. C is not the correct answer. Anything else? Yes, B is the correct one, global optimal solution. It gives the global optimal solution, but it takes a lot of time to convert. So it gives the best possible outcome of the results, best possible results, but the computation it is not a low computation burden. It has computation burden and not also simple in formulation. So this global optimal solution is the right answer. So direct cause of the failure of the lithium ion battery: damage to ACI layer, leakage current, Coulombic efficiency, heavy operation. A, A, A1, A. Okay. So damage to ACI layer, leakage current, Coulombic efficiency. So ACI layer is the it is a mainly a interfacing layer. It's for those. It's, it is also known as solid electrolytic interfacing layer. So this is the correct answer. Damage to ACI layer. Indication of state of charge SOC of a battery is best given by specific gravity, temperature, or level. Yes, it is specific gravity of the electrolyte. So, so, so this is the first. This is the this week's discussion, and these are the questions that are being discussed based on the uh, previous year's question and solutions. So, so this is the assignment one. So previous last 2 weeks we can't discuss about these assignments. So uh, these are the direct questions. The questions, the answers can be directly found. These are quite direct questions of the assignment. So if you have any kind of doubts, you can ask, or else we would be. The reason is given. So for those who have not gone through yet, on they must surely go through these assignments, as the questions in the exams would be getting somewhat near to this, not exactly the same, but still you can refer to this as a pattern which can be followed for the exams also. So this was clearly, it is from 22 to 200 kilowatt, and energy range for commercial customer. It is from 20 to 200 kilowatt. And then we have the grid assets are bought and sold in the market domain. It is also quite obvious. The boundaries of the customer domain, both utility meter, it is from the lecture itself that the boundaries are both of them from the boundary of the customer domain. Okay, the ESI, energy service interface, it is mostly dealing with the customer interface to which domain. Out of these, it mostly deals with the customer. So customer is the right answer. Justifications are quite given. Last week, somebody was asking to they were having some questions, queries regarding these assignments. So I couldn't discuss those days last week. So domain is responsible for smooth operation of the process. Operations domain, entire operation domain is responsible. And electrical distribution system. Today also we have discussed that distribution system is mainly distribution system, radial, looped and meshed. But in general, it is radial or weakly meshed. The One Grid, One Nation, One Frequency Act came into picture from December 2013 itself. One Grid, One Nation, One Frequency. When the southern high voltage southern grid, when the southern grid got connected with the east west north south grid on December 2013 itself. So this is the justification 31st December. Now the commonly used fuel cell is hydrogen and oxygen. The input is hydrogen, and oxygen is hydrogen and oxygen is input, and out the emission is water vapor, means the that is being ejected from the system is water vapor. Then the regulate tariffs is the CRC, Central Electricity Regulatory Commission, and State Electricity Regulatory. They only regulate the tariff of the state and central level policies, and major amount of losses takes place in mainly the losses takes place in the distribution. The entire main mostly the losses take place in the distribution because the distributions have the R by X ratio high. That means the R is high in distribution. So when losses are directly proportional to I square R. So power loss. So what we can identify is that the distribution system has the most amount of losses. Okay. So this is the assignment one. This is the assignment two. So a SCADA consists of human machine interface HMI. So it is placed in the master session. Then we have the which of the following components present the presents data to the master session. It is data processing application DPA. Also, it's not a advantage. So this is a careful means for the exams also. These types of questions do come. So where we have it has no moving part. Okay. These are cadmium telluride PV technology. This is quite a direct question where the 9 to 12% of the efficiency, and then which is not a cause of the series resistance of a solar cell. So manufacturing defects is not a cause because this is due to the shunt type, which is not a cause of series. So all these are cause, but manufacturing defect is not the cause because these manufacturing defect due to these manufacturing defects, the shunt resistance are being modeled into the PV system. Okay, solar cell design, which is the most expensive part of a PV system. So most cost it is associated with the PV array. It was given in the lecture part as a part of lecture. So around 57% of the total cost is okay, it's given here only. 57 of the cost and the battery storage as 30% of the cost. So 80% of the cost is being incorporated in these two places of itself. Wind energy supports the weight box. It's a low speed shaft. And which of the following which of the following characteristics affect the characteristics of the solar cell? So it's both solar irradiance as well as temperature because it was directly from the last discussion. It's a direct question. Then we have this is both of these because both solar irradiance and temperature we have observed. And then we have the nacelle which does not consist of wind vane and anemometer are not a part of the nacelle. Okay. All these things are a part of the lesson. And, and this is the last part, last question. So external wind does not depend on which of these. So turbine radius, because speed, wind speed, swept area, everything are dependent. So only one is left, that is turbine radius, not dependent on these. Okay, so that's it for today's discussion. So all the people who are joining now can join the next session if they are willing to join, because we have a session from 6 itself, and these two session this third week session is over, so you can join the next session from 6 to 8. I think you mistakenly join this session.
Hello, good evening, sir.
Yes, good evening, good evening.
Can I have a request?
Yes, yes, yes.
Can you please share the recording of all the earlier sessions? Like, I mean, many a times it feels a bit difficult to attend the session at the prescribed time, right?
Yes, okay, okay. But I think I have also seen that in the smart grid advanced technologies, this means in your portal itself. So you can now log in. I have seen the tab of the problem solving discussion. So you will find that problem solving discussion tab or the problem solving recording video tab in your profile. Means where you have that week one, week two, week three, and week four. All these things are given, right? So at the last option, you will find that one new section has been added, which is dealing with the problems for problem solving recorded videos of the lectures. So you can directly click on those, and you can find the recordings of all the three TAs. Means as a part, means you can go through any means whenever you want to. You don't if you have any kind of issues, because many of you are working professionals, so if you don't have time, you can see the videos itself. Okay.
Okay, sir. Thank you. And
Ah,
sir, I found question number 9 of the assignment 2
question number
pertaining to that wind vane.
wind vane. Acha, okay.
Yeah, yeah. I mean, the question was a bit ambiguous. Like, I mean,
Ah,
it is mounted on the nacelle itself, right?
yes, it is mounted, but nacelle itself, but
It is not within, that's what it is, but
it
then
is
it
not
is,
within. Yes,
yeah,
yes.
but then it seems like the question was a bit ambiguous.
Yes, it has been given pertaining to the context that it is not inside, means
Yeah,
uh,
yeah, that's what
anemometer
it
and
is.
wind. Yes, yes.
Yeah, it is to be understood, but then,
Ah,
like, it
yes,
is,
yes.
yeah.
Uh, you can say, but means the main aim of framing this question was from that context itself. So yes, yes, you will have to just sometimes cope up with some of the scenarios. So
Okay,
yes,
sir, thank you.
okay. Thank you very much. Thank you. Thank you. So let's close this today's session, and we would meet on next Saturday 4 to 6. So thank you.